do you grow 1.5 million salmon in open ocean? No shoreline, foundation, or nearby power plant. The answer looks more like an offshore oil rig than a farm. A 110-meter semi-submersible hull, a turret that rotates the whole structure with wind and current, subsea power cables, cameras counting every fish. Each cage holds up to 1.5 million salmon. Every component has a reason. We'll go through them one by one.
When people hear fish farm, this is the image that comes to mind. Sheltered fjord water, a small ring of net cages, a farmer in waterproofs feeding salmon by hand. That picture only captures a small part of the industry today. Now zoom out, way out. The Hav Farm Jostein Albert stretches 385 meters long and 59.5 meters wide, longer than most commercial ships. It rotates a full 360 degrees around the tip of its bow to face changing weather. 6 nets hang up to 56 meters deep. Capacity, 1.7 million salmon. Power, 100% electric. A structure that size does not just appear at its location. It has to be towed there. Multiple heavy-duty tugs link to the Hav Farm via high-tension cables. Ballast pumps adjust buoyancy. Lifeboats are launched. The convoy moves slowly through Norwegian fjords toward open sea, a coordinated marine operation involving dozens of vessels. Different shape, same shift in scale. Ocean Farm 1 is a semi-submersible rig 110 meters across and 69 meters tall, weighing 7,700 tons. It is engineered to hold up to 1.5 million salmon and withstand powerful typhoons. A central control block rises above the ring, and before fish can enter the cage, engineers have to answer one question: what shape can survive the open ocean without turning the fish cage into a wreck? 3 completely different shapes, 3 answers to the same impossible question. How do you survive the open ocean? The first answer came from a Norwegian design team in 2015. Their idea was to make the farm long, really long, and let it spin freely with the weather instead of fighting it head-on. At 430 meters long and 54 meters wide, a Hav Farm hit broadside by ocean waves would tear itself apart. The solution is a turret mooring at the bow. The entire structure rotates around that single anchor point, so the largest waves and currents always strike from the front, never from the side. 6 cages hang along the hull, holding up to 10,000 tons of salmon. The second answer rejects long and rotating in favor of round and symmetric. Ocean Farm 1 is a circular semi-submersible. Where Hav Farm spreads load across length and rotation, Ocean Farm 1 spreads load across an entire ring. Built in China and towed to Norway, it sits in deep coastal water as one continuous geometric form. A round structure has no weak side. Waves and currents hit it the same from any direction, and pressure spreads evenly around the entire perimeter. Ocean Farm 1 measures 110 meters in diameter and 69 meters tall, weighing 7,700 tons. It can hold 1.5 million salmon. The platform is rated to survive winds of up to 36 meters per second typhoon strength. The same circular logic appears in composite designs. The Neptune cage is built from glass-reinforced polymer in a massive cylindrical form. A floating crane lifts the entire cage off the shore directly into the water. The round geometry handling all directional forces the moment it touches the sea. The shape distributes loads around the structure instead of concentrating them at a few critical points.
The loadout of Arastrates 1 provides a useful visual comparison. Its circular semi-submersible arrangement follows the same engineering logic: distribute forces around the structure and keep buoyancy where it contributes most to stability during offshore operation and transport to site.
Choosing where to place a farm is only part of the challenge. Keeping it stable there is another. Semi-submersible spar concepts use ballast systems to adjust draft for operations, maintenance, or storms. Stability comes from buoyancy positioned deep below the surface, reducing motion at the cage level while preserving access for feeding, transfers, and inspections at sea.
The third answer rejects holding still entirely. Rather than remaining fixed, Ocean Ark proposes a self-propelled trimaran that can relocate gradually toward better water conditions, reducing exposure to unfavorable environments while maintaining offshore production.
But a design on a screen does not survive the ocean. It has to become steel, cut, welded, inspected, coated, assembled, and tested in a yard ship. At a Turkish yard, technicians inspect every seal, every penetration, every mounting point. Silicone grease is removed from joints before pressure tests. Nothing leaves until each fitting checks clean. The steel hull is only half the structure. The other half is the net, and the net is woven, sewn, and assembled in a different kind of factory entirely. Automated weaving machines run continuously. Massive HDPE pipes are welded into floating rings. Hand stitching reinforces every load-bearing edge. The strange thing is that the softest part of the system, the net, may be just as critical as the heaviest steel. Washing, repair, quality certification, dimensional measurement, chemical impregnation, drying. Any failure in this chain means escaped salmon, a biological event the entire industry cannot afford. The softest part of the system is treated with the highest discipline. A cage built for typhoon waters has a different problem. Hainan, southeast China, waves up to 11 meters during monsoon season. The cage cannot just float through that. It has to sink below it. The submersible cage assembles like a standard sea cage, but adds a ballast and buoyancy system inside the structure. Opening a series of valves takes the cage from the surface down to 10 to 15 meters underwater in under 5 minutes. Compressed air refloats it in 10 minutes. The interior knotless net is made from UHMWPE, a polymer fiber stronger than steel by weight. Material choice transforms how a net behaves under load. Copper alloy mesh is now used at large salmon sites in Patagonia, Chile. The metal weave resists biofouling without chemical cleaning, blocks predators like sea lions without a separate predator net, and survives multiple grow-out cycles without replacement. Divers handle only the remaining 10% of cleaning work. The net itself adds weight that stabilizes the entire cage against wave motion.
The empty steel hull becomes a working factory only when the systems go in. Cameras and sensors mount inside the cages. Machine learning runs underwater to count sea lice without netting fish. Biomass and fish weight distribution are tracked in real time. Operators can monitor conditions continuously without entering the cage. Feeding lines deliver pellets automatically based on fish behavior. All data flows to remote operation centers, one centralized cloud platform across hundreds of pens. The system compares information from multiple sites at the same time to identify changes quickly. Animal welfare alerts route directly to on-site specialists for intervention.
One feed station now controls 4 sites simultaneously. AI tracks pellets, fish activity, and feeding behavior in real time. 2 staff per shift handle everything that used to require teams on every individual pen. Much of the daily decision-making is now supported by continuous data rather than direct observation alone.
High-quality underwater video and continuous sensor streams need bandwidth beyond 4G. 5G connectivity transmits massive video and sensor data from each cage to cloud and edge analysis platforms in real time. This allows operators to receive near-instant updates from sites located far offshore. Large volumes of information can be processed continuously without waiting for manual reporting. A clean net allows water flow. Water flow delivers oxygen, and oxygen keeps the fish alive. Cavitation jets strip biofouling from the mesh without harming a diver's skin. Norwegian Standard 9410 requires seafloor samples before restocking and at peak production. Inspectors measure pH, redox, sediment color, smell, and animal life. Samples score from 1, best, to 4. The reported figure, 94% of Norwegian fish farms hold very good or good environmental status. The results help determine whether a site can continue operating under the same production conditions. A 385-meter steel hull cannot just sail to its destination. It rides there. The Boca Vanguard carried the Hav Farm Joe Stain Albert 385 by 60 meters, making it the largest single cargo ever transported by ship. Arriving at its destination is only half the journey. To launch the Hav Farm, Boca Vanguard begins a controlled ballasting operation, flooding its internal tanks until the deck sinks below the waterline. Slowly, the giant structure lifts free from the vessel that carried it. Tugboats move into position as the Hav Farm floats independently for the first time, ready for the next stage of deployment at sea. This kind of scale is no longer unique. In Guangdong, the Highway No. 2 platform measures 86 meters long, 32 wide, 16.5 tall. It is rated to survive Category 15 typhoons, the strongest classification on the regional storm scale. Other designs avoid the heavy lift problem entirely by allowing the farm to be relocated by tug. The Lingding Ranch No. 1 platform off Zhuhai can be towed along coastal routes under its own ballast system. It lowers and raises itself, supports remote control, and runs on integrated wind and solar power. A third approach skips heavy lift transport completely by keeping the farm small enough to be moved by an ordinary tug. In New Zealand, researchers are testing a relocatable fish pen for true open ocean aquaculture, far from land, in deeper and rougher waters than conventional farms operate in. The first prototype is moored on a single point. The enclosure swings around that one anchor point as wind and current shift, much like a weather-vaning hull, but at a much smaller scale. The system was born from a different question. How do you move juvenile snapper around cheaply when road transport is expensive? The answer was to feed them at sea and let them grow inside the moving pen. That single decision changed the entire design philosophy. The fish would be raised in optimal conditions year-round by relocating to better water rather than enduring fixed conditions. 2 species are being studied so far, snapper and king salmon, measured for preferred temperature, preferred flow, and welfare under open ocean wave energy. Each finding feeds directly back into the next iteration of the pen design.
Getting the structure into the water is one thing. Holding position in the open ocean is another. Once the anchors go down, the goal is not to stop movement, but to control it. An offshore farm must move with waves and current without drifting away. Tension lines spread forces across the structure. When current pushes against the net, the cage shifts slightly downstream, while the overall shape remains stable. Before anchors hit the seabed, divers do not go down. A compact ROV does. The vehicle drops from a small surface boat, descends along the planned mooring line path, and films the bottom in real time. Engineers use the footage to verify seabed conditions before any equipment is installed. Offshore installation is not one operation. It is dozens of smaller installations stacked on top of each other. A specialized vessel arrives with rolls of net and lines on deck. Cranes lower the net into the cage. Technicians tie knots, measure distances, fit hard polymer parts at the tunnel base, and connect every anchoring rope. Once the structure is anchored, the next installation problem is electricity. A diesel generator was the old answer, loud, expensive, and at constant risk of fuel spills. The new answer runs power directly from the onshore grid through subsea cable. The diesel generator stays on board, but only as emergency backup. Service boats can plug into the cage to charge while operating. The same shift is happening at much smaller scale. Solar inverters now power coastal fishing boats and aquaculture rafts in Peru, delivering 24-hour electricity, cutting fuel transport burden, and silencing the diesel engines. At a land-based salmon facility in northern Denmark, that approach is built into the site from day one. Wind turbines and solar panels supply the operation. Seawater is filtered and recirculated rather than dumped. Waste becomes energy. The result is salmon raised year-round without antibiotics, hormones, or external parasites. Much of the production environment can be controlled more precisely than in open water farming. A final approach rejects the entire concept of mooring. A 170-meter farming vessel runs 3 electric or diesel-electric engines at up to 4,000 kilowatts. It self-positions at 4 knots, seeks the best water for the fish, and steers away from incoming storms. Copper-zinc alloy cages resist biofouling and predators. The farm holds its place by moving, not by being tied down. Steel in place, anchors holding, and power flowing. The offshore farm is ready for fish. The hard part starts now. turning an offshore structure into a place where fish grow every day. Before entering offshore cages, fish spend their early months on land. A 9,700 square meter hatchery produces up to 6 million smolt each year. Fish weighing 120 to 130 grams move through closed pipes from breeding tanks to a docked wellboat, reducing stress during transfer.
Moving fish between tanks sounds routine, but delays and rough handling add stress that operators try to avoid. At a Danish land-based salmon facility, a portable fish pump simplifies that task. Staff connect hoses, test the system, and begin transfers with little preparation. The pump handles fish weighing up to 2 kilograms and operates week after week with minimal maintenance. Simple replacement parts keep downtime low. Workers spend less time preparing equipment and more time watching fish condition during every move.
Once aboard the wellboat, smolt enter a closed-circuit transport system that monitors every parameter. Negative pressure draws fish into the cargo hold. Counting devices register exact numbers. Sensors log oxygen, carbon dioxide, ozone, pH, and temperature continuously. Water is recycled, oxygenated, and skimmed clean of waste throughout the entire voyage to the offshore site. The first stocking arrived at the offshore Hav tank. 68,464 salmon at an average weight of 5.1 kilograms were transferred from the neighboring Bratoi site. Years of construction, towing, mooring, and commissioning ended in a single transfer. The Hydra project moved from build phase into full operation. Behind every pellet entering a cage stands an industrial chain stretching across the country. Raw materials are milled, sieved, and pressed through dies of different sizes. Robotic arms stack bags onto pallets. Every batch is sampled, ground, and analyzed against a nutritional spec sheet before leaving the plant. The same logic appears at every scale of aquaculture. A feeder spinning pellets across the water surface in a wide arc. At the offshore scale, feeding is its own engineering subsystem with multiple layers. Pellets sit in tall silos aboard a feed barge moored next to the cages. Operators in a central control cabin run the entire process from screens. Pneumatic blowers pressurize air inside enclosed pipelines. Selectors route the pellets through individual feed lines, one for each cage. At each cage, a rotary spreader scatters pellets evenly across the water's surface. Underwater cameras stream live footage back to the cabin. Live readouts show depth, temperature, voltage, and heading. The operator adjusts feed rate based on what the fish actually do. An AI vision module now decides feeding timing instead of fixed schedules. When the fish are inactive, no pellets are released. Less waste, cleaner water, longer biofilter life. Cameras continuously monitor fish behavior inside the tanks. Feeding resumes only when activity levels indicate the fish are ready to eat. A modern offshore fish farm operates more like a control center than a collection of cages. Cameras watch feeding activity, sensors track water quality, and software links every system into a single network. On land, recirculating treatment equipment cleans and reuses water through multiple filtration and oxygenation stages. Offshore, environmental sensors, underwater cameras, automated feeders, and net cleaning machines work together around the clock.
Data flows continuously back to operators, allowing faster decisions and tighter control over fish health, feeding efficiency, and daily farm performance. Oxygen is the one parameter that cannot be allowed to drop. Fish die fast without it. A mobile drop-in unit deploys directly from a boat. Twin oxygenation units float on individual buoys. A built-in pump starter, dosing unit, and cable drum sit on a single pallet. Crews handle short-term oxygen demand and emergency situations on demand. The system can be positioned quickly wherever additional oxygen support is required. Inside the cage, water never sits still. It must flush continuously, carrying waste out and oxygen in. A green dye test reveals the actual flow pattern. The dye spreads from the center, expands across the cage, dilutes as it reaches the perimeter, and exits with the natural current. The ocean does the work. Healthy fish are only half the work. The harder half comes next, moving millions of pounds of living biomass off the platform without breaking it. A specialized vessel with onboard oxygen production, carbon dioxide removal, and diesel-electric engines pulls alongside the farm. Tanks up to 3,200 cubic meters hold live salmon under controlled water chemistry during transport to processing facilities ashore. Pumping the fish out is not the first step. Gathering them is. Workers on small support vessels surround the circular cage and begin handling the net by hand and pole. Yellow marker buoys are lowered into the water to guide the fish toward one corner. A large transport line with flotation rings is stretched across the cage. The inner net is then drawn tighter and tighter, herding the salmon into a concentrated zone. Once the density is right, thick black suction hoses descend from the wellboat into the crowded section. The fish are pumped directly from the open water cage into the ship's holding tanks. The pump itself does the lifting. A shore-based pump creates suction through a white hose dropped directly into the cage. Fish and seawater flow upward together. A separator on the dock returns the water to the sea. The same vessel architecture appears in non-harvest operations too. A processor-class boat ties up beside the cage. Large red and black hoses connect from the net interior to the deck. Fish flow continuously between the cage and onboard processing chambers. The arrangement allows large volumes of fish to be handled without repeatedly lifting them from the water. 3 workers in red safety gear stand at the edge of the crowded holding cage. A large blue intake pipe descends into the water. Fish and water are drawn up into a pump house on a floating platform, then forced through an orange high-pressure line directly to insulated tanker trucks waiting on shore. A different processing logic kills the fish at the cage instead of transporting them alive. Salmon are pumped through a countercurrent tank, then onto a conveyor passing between an electric stunner's negative and positive charges. Laser-positioned camera systems direct robotic blades to make a clean gill cut. Cooling tanks complete the bleed. On shore, the entire process, from live fish to packed box, takes under 2 hours. Fish are stunned by electric current, hand-bled, gutted, washed, and chilled in sequence. Automated grading sorts by size and quality. Each box is weight-checked, ice-topped, sealed, labeled, palletized by robotic arms, and loaded onto refrigerated truck. Inside the processing plant,
the salmon enters a fully automated production line. Bellies are cut and vacuum gutted. The fish enters a spiral chilling bleeding tank that combines cooling, bleeding, and deep washing in one rotation. Electronic scales grade each fish by weight into separate channels. Boxes are fed in automatically, filled, check-weighed, labeled, and finally palletized by robotic arms ready for distribution. Comparable plants for other species push the automation level even higher. Fish are held in a large tank, weighed entering the factory, and fed onto a sorting line. Cameras inspect each fish from both sides: quality, quantity, species. Damaged or incorrect fish are automatically discarded. A weighing station forms exact batches that are vacuum sealed into poly bags, loaded into freezer trays, frozen at 1 ton every 3.5 hours, packed 2 blocks per carton, strapped, labeled, oriented onto pallets, and shrink-wrapped. Most of the product moves through the facility with minimal manual handling. Production data is recorded throughout the process to support quality control and traceability. An offshore farm is not built once. From the day fish enter the cage to the day they leave, the structure has to be defended every single day against salt, growth, fatigue, and time. Norwegian regulations spell out exactly what the sea phase demands. Marine facilities must prevent fish from escaping under strict regulatory requirements. Operators must handle storms, sea lice treatment, disease, predator attacks, and toxic algae or jellyfish blooms throughout the entire grow-out cycle. Biofouling must be removed from the nets so that water flow inside them remains good. A clean net is what keeps oxygen reaching the fish. Good husbandry must be ensured, biosecurity safeguarded, and the cage system inspected continuously. Every component, from the mooring lines to the net panels to the feed pipes, requires periodic checking and replacement throughout the production cycle. Maintenance is not only about steel and netting, it is also about what lives on the fish. A 6-line hydrolyser system processes 200 tons of fish per hour. 2 stations sit on each line. 3 drum filters and screen plates strain out every parasite particle down to 100 microns in size. A central control room manages the operation via camera feeds. 1 operator monitors the entire flow. Gentle pumping moves fish through each station without injury. The output? Fish stripped clean of lice, return to the cages healthy and feeding again. The same maintenance pressure exists wherever cages float in deep open water. A 383 square kilometer high-altitude reservoir holds roughly 200 deep wave-resistant cages, producing close to 10,000 tons of trout annually. A smart remote feeding platform tracks water temperature, dissolved oxygen, pH, fish count, and fish size in real time. Each cage holds over 20,000 fish at peak. Daily harvest hits 20,000 fish processed at the lakeside plant. Every cage, every sensor, every feed line, and every mooring point demands continuous inspection across the long production window. Maintenance crews move constantly between production areas to verify that equipment is functioning correctly. Small issues detected early are easier to correct before they affect fish growth or operations. The hardest part of net maintenance is biofouling,
and one project rebuilt the net itself to solve it. The Velella Drifter pen floats in 12,000 feet of water off the Big Island of Hawaii, riding back eddies behind the island. Its submersible pen uses brass mesh instead of conventional polymer netting. The brass eliminates biofouling on the mesh surface entirely. Drag drops. Water flow through the cage improves. Cleaning frequency falls to almost nothing. The cage carries 2,000 fingerlings of native Kona kachi raised at a coastal hatchery and stocked offshore. A different solution shrinks the entire maintenance burden by changing the platform itself. A fully autonomous oceanic vessel runs both coastal and offshore production, actively seeking the best water for the fish.
A more radical design abandons conventional cages entirely. Aquapods are giant underwater mesh domes. Fish school inside them as they would in the open ocean. Waste disperses naturally through the spherical structure. The shape itself reduces the maintenance burden that flat-walled cages impose. Water can circulate freely around the enclosure from multiple directions. Fewer structural surfaces are exposed to the same build-up patterns seen on traditional cage designs. Maintenance discipline begins on land long before the first cage is touched. A modern RAS smolt facility filters, disinfects, and recirculates every drop of water before fish enter the tanks. Disease-causing microorganisms are blocked at intake. Density is monitored continuously. Operators regularly review system performance to keep water conditions stable throughout production.
The maintenance playbook does not stay still. Year after year, new regulations, new inspection technologies, and new sensor systems reach the industry. Each season demands updated protocols. Coatings improve, ROV cameras grow sharper. Predictive software flags fatigue cracks before they spread. Digital records now allow operators to track maintenance history across entire farm networks. Inspection data from different systems can be combined to identify trends before failures occur. Each component of an offshore farm, from anchor chain to net panel to feed pipe, runs on a maintenance cycle that the operator must execute on schedule every year without exception.
Across the world, the systems built to feed billions of people are quietly being redesigned. Floating pens hold around 700,000 fish at a single site. Pellet composition has shifted from primarily wild fish to only 15 to 20% fish content over 20 years. Underwater cameras now watch when salmon reach satiation and stop the feed automatically. Strong tidal flushing carries waste back into the food chain. Local aquaculture replaces collapsed commercial fisheries with year-round work. The result is a production model that relies increasingly on monitoring, automation, and resource efficiency.
A decade ago, the future was a single semi-submersible platform built from offshore oil and gas technology. Today, that platform cultivates more than 1.1 million salmon in Norwegian open water.
The next horizon goes further still. The farm itself becomes mobile, untethered from any single location, capable of chasing optimal water year-round. A New Zealand research team set out in 2016 to build a relocatable fish pen capable of true open ocean operation. The original idea came from juvenile snapper logistics. Road transport was expensive, so the team asked whether young fish could simply be towed at sea and fed along the way. That question became the founding concept. Move the fish around, Keep them in optimal conditions year-round instead of forcing them to endure whatever conditions arrive at one fixed point. The first demonstration is a moored system. The enclosure rides a single-point mooring and swings around it freely as wind and current shift. The setup pairs a fish enclosure with a support and monitoring buoy carrying feed and instruments. Researchers studied snapper and Chinook salmon to understand what each species needs for optimal growth, preferred temperature, preferred flow. Open ocean conditions differ entirely from sheltered fjords. The pen design starts with biology, not structure. The longer-term vision is true open ocean, far from land, possibly out of sight of any coastline.
A second future model integrates every stage of the cycle under one company. Japan's Salmon Farm runs a hatchery near a forest mineral source, an onshore Fukurara farm at the coastline, and 2 offshore farms at Imabetsu and Fukurara using large circular pens in open water.
Future farms also depend on what goes into the fish. A specialized mackerel-shaped pellet for bluefin tuna replaces live bait. Around 10 tons of engineered pellet now match the growth output of 30 tons of traditional live bait, a step change in feed efficiency.
The number behind that feed innovation is severe. Wild adult bluefin tuna populations have fallen 80% from their late 1990s peak. Farming offers one of the few practical responses to that collapse. The challenge inside the cage is the tuna itself, extremely selective eaters that instinctively ingest prey head first. Each pellet is shaped to mirror a mackerel, with a small nose at the tip signaling where the front is, an outer layer wrapping nutritional essentials like fish oil, fish meal, and vitamins inside. The design encourages the fish to recognize the pellet as a familiar food item. Consistent feed acceptance is critical for maintaining growth rates and reducing waste inside the farming system. One answer to the future searches for places where the ocean is already perfect. The Uakai Sea in southwestern Japan offers stable water temperatures, depth, and excellent flow nurtured by the warm Kuroshio Current. 30 large cages spread across 2 locations 25 kilometers west of the city. Cages are sized to let fish swim freely, minimizing stress and ensuring exercise. The full harvest cycle, from lifting to chilling, completes within 120 seconds. Hygiene control runs through HACCP certification at every processing zone, with color-coded equipment preventing cross-contamination. Environmental conditions are monitored throughout the year to support consistent production. Fast handling and strict processing standards help preserve product quality from harvest onward. Every cage operating today is being remade, feed by feed, sensor by sensor, traceability layer by traceability layer. The future of fish farming may not look like a farm at all. It may look like a ship, a platform, a factory, and a biological control system combined. Humans are no longer just farming near the ocean. They are trying to engineer a farm that can live inside it. That's it for this one. If watching real machines do real work is your kind of thing, hit subscribe and we'll see you on the next build.